All right, here we are for another biology video. This will be a short one to wrap up the radiometric dating idea. In the last video, we talked about how we find the age of a rock using radiation. Um, this video is going to focus on some of the more details about how it actually works and how there's usually questions that come up when we talk about this kind of thing. And again, it's important that you understand the idea of radiometric dating because so much of our understanding of evolution comes from fossils and knowing the ages of those fossils so that you can put them in order and be able to figure out the evolution of life on Earth, right? Again, think about how hard it would be for the Cominalcule lab if it didn't tell you how old each thing was so that you didn't know where on the lines to put it, right? Like that would be super difficult. So it's really important that we know how radiometric dating works. Now, to remind us a little bit of how it works, you have a rock like this, and it has some radiation in it. Let's say it has 20 pieces of radiation. Let's say it has 20 pieces of uranium-235. At the beginning, it has 20 pieces of uranium and 0 pieces of lead, which is what uranium turned into. After some sort of time called a half-life, which for this one happens to be 704 million. Half of those atoms will lose their radiation. They will shoot out particles and the radiation will be gone. So we started out with 20 uraniums and now we have 10 uranium and 10 lead. Then after another 704 million years, half of those 10 went away. So now we only have 5 left. Those 5 became lead. So now we have 15 lead. And it just keeps getting cut in half every 704 million years, or again, whichever half-life we happen to be talking about. Every half-life, half of it goes away. We can measure what percentage there is left in the rock and then use that to figure out how many half-lives have gone by and how many years have gone by, right? That's the basic idea. But for that to work, there have to be some assumptions that are being made, some things that have to be true. And I'm going to keep using this idea of the hourglass to show the analogy of how it would work with the radiometric dating. So the first thing that's important is that the rate of the radiation needs to be predictable. In terms of the hourglass, this means that the sand has to fall at the same rate, right? Imagine if you have an hourglass and it's full of sand up to here and it takes an hour for it to fall on Mondays. But then for whatever reason, on Wednesday, you come back and the sand is falling faster than it was before. Again, why would that happen? Hopefully it's not, but if it was falling faster, this would make it seem like time was going faster. The sand would all leave the top earlier and you would think an hour had passed, but it wasn't an hour. It was actually much shorter than an hour. Or for example, what if the sand was falling slower, then it would make the sample seem older because it would take longer for the sand to fall and it would take more than an hour, right? So that would change our timing. What if there were already, so it says there should be no daughter atoms present at the formation of the material, meaning if there's already sand at the bottom, right? It should be every piece of sand is at the top and then it takes an hour for them all to fall down. But if some are already at the bottom to start with, then it would seem like it would take an hour for all the pieces to fall, but it was actually less than an hour, and it would make it seem shorter. And so this would be a problem as well. And this is actually the main one that people are most interested in, and we'll talk about that the most. The last thing is that you can't lose or gain atoms or lose or gain sand. Imagine you're having your sand grains fall. They're falling at the normal rate. Everything's fine, but someone or something is adding more sand into the top as you go, right? And so it's going to take longer for the sand to go through. It's going to seem like it took an hour, but it actually took more than an hour because more sand fell than was already there. Or for whatever reason, maybe somehow some sand is being removed as the sand is falling. This would make it seem like there was a shorter time than an hour, right? And so these are all things that would mess up an hourglass, and they would also mess up radiometric dating. So I'm going to go through these very quickly about how it actually applies to the rocks. So the first one is that the rate of decay must be predictable. The good thing is that half-lives are well understood and well measured, and we can actually measure this with our own instruments. This is not a guess. We know exactly how they are. The other part about it is that, well, maybe it goes slower when it's cold or something like that, right? So during ice ages, rocks would lose their radiation slower, and so this would make the rocks seem like a different age than they actually are. But radiation is not changed by temperature and pressure or anything like that. In fact, radiation is one of the most consistent phenomenon that happens. Again, we don't know exactly when each individual atom is going to shoot up its radiation, but on a statistical level, when you average it all out, it all comes out very even. This is because radiation is because of something called the weak nuclear force, which is one of the 4 fundamental forces in the universe that holds everything together, along with gravity and electromagnetism and the strong nuclear force. This is all way above our pay grade, but the idea is that this doesn't change. This is something that must have always been the same, and therefore we don't have to worry about the radiation coming out faster or slower depending on the situation. So assumption 1, that should be pretty safe. Now, assumption 2, again, was the one that has the most questions most of the time. What if there was already daughter atoms present in the material? So what does this mean? Let's say that you find a rock that has 35 atoms of uranium and 65 atoms of lead, right? The uranium has been turning into the lead this whole time. We are assuming that that meant that there was 100 pieces of uranium at the beginning, right? 35 plus 65 makes 100, right? So we would think that 35% of the radioactive elements are around, and that would make us be over here at about 1.5 half-lives, right? But what if actually, because we couldn't know this, like if this has been going on for 704 million years or whatever it was, how do we know what it was actually going to be, what we started at? What if there was actually 70 uraniums and there was already 30 atoms of lead to begin with? So instead of actually going from 100 down to 35, we only went from 70 down to 35, right? And so this would mean that a much smaller amount of the radiation had gone by, right? It would be something like up here. And so the rock was actually only a half of a half-life old, right? It was only 300 million years old instead of a billion years old or whatever it is, right? Like this is definitely going to be a problem. It would seem that the rock was older than it already is. Now, this is a real problem for dating rocks. Which is why we only usually focus on one kind of rock called zircon. A zircon is a rock that looks like that. It's one of the most common minerals in the earth. It's made out of a zircon and a silicon and 4 oxygens. You don't really need to know that, but you are going to see a diagram of this in a second here. It's very similar to just quartz, which is like one of the second most common material in the crust. Like it's part of sand. These are very common rocks, which is good because they're everywhere. But the thing about zircon is the way it's made. It has this zirconium atom in the middle, and then it's connected to 4 oxygens. Then there's a silicon that's connected with some more oxygens, and there's an oxygen over here, and that goes off in that direction. And then it repeats over in the other side. So here's the silicon with the 4 oxygens right there, and here's another zirconium with the 4, and there's another oxygen right there. And it just keeps going, right? This is called a network. It's like a grid or a web, and this is what rocks are made look like kind of at the molecular level. But here's the thing. Uranium can sometimes take the place of the zirconium, right? So as the rock is forming, sometimes a uranium will sneak in instead of a zirconium, right? And this is where the radiation in the rock comes from in the first place. Over time, the uranium will turn into lead, right? So now the rock has lead in it. It didn't have lead at the beginning, it had uranium, now it has lead. But what we were saying is maybe there was already some leads in here. So it looks like it was a uranium that switched to lead, but it was already lead. But here's where some chemistry comes in. It turns out that the chemical properties of lead don't mimic those of zirconium. So while a uranium will sometimes take the place of the zirconium, the lead will not. It doesn't fit in there. And so you shouldn't ever have a piece of lead inside a zircon rock. So as long as you stick to those rocks, then you should be pretty safe, right? And so the zircons, you don't have to worry about any lead being in there. This means that they're the best ones to use. So people have been looking for the oldest rocks everywhere. The Jack Hills rocks over in Australia. It's just like this kind of small hill range, not a mountain range, not big enough for being mountains, but these are some really old rocks. But the rocks themselves had little pieces of zircons inside of them. Like basically these rocks here are kind of like they're sedimentary, like it says, which means basically sand has been smashed together to the point where it's so kind of fuses together to make a rock, right? And so sedimentary rocks are made out of little tiny pieces of other rocks. So we don't have any full on like old rocks, like a big old chunk that's super old. But this little piece of rock that was found in these old rocks is 4.4 billion years old, right? So that means that this rock has been around for 4.4 billion years. The Earth has to be at least that old. And usually it would take at least a little while for that to form. So this number sometimes gets bumped up to 4.5 or even 4.6 billion years old for the age of the Earth. And then we have some other evidence for that as well that we're not going to get into now. But can we trust the zircons so that we know that they're the age they are? Chemistry and physics would seem to say, yes, we can. Now, finally, one last one. There's no loss or gain of atoms. Let's say that should say 35. That was a mistake, right? You have your rocks. If you heat the rock, it will cause the atoms to fly away, right? And so rocks that have been heated up will seem younger than they actually are. This is a real problem, especially considering the Earth. It is still active, right? So there's like volcanoes, and there's still parts of the Earth are being pulled down into the center of the Earth, or not to the center, to the mantle, it's called, and they melt. And so when rocks melt, it resets the timer, right? So the birth of a rock would be when the rock like solidifies into its actual rock form. So melting rocks is bad. Heating rocks can be bad as well. Contamination of rocks also will happen if somehow just like some lead just like gets smashed into it somehow, like over time some atoms just get fused into the rock. This would make them seem a different age, right? But back to the zircons. Zircons are resistant to all sorts of different things, and so there should be minimal loss of material. They don't, unless you completely melt it down, it won't lose its uranium. So again, the trick would be to find rocks that haven't already melted, which again, sometimes rocks, the crust of the Earth does get melted sometimes, which is why it's hard to find really, really, really old rocks. That place over there in Australia just happens to be one area that has never gotten melted since the beginning of the Earth, basically. And so the zircons we're pretty safe to assume that they haven't been contaminated or they haven't been heated to lose any radiation. So the zircons tell us a lot about the ages of rocks, but then we can take these ages and we can use the law of superposition to figure out the other rocks, right? So like there are some rocks that are bad candidates for radiation dating, radiometric dating. But if you can figure out the age of one layer, right? Like, so for example, you know for a fact that this one, or actually I think there's gonna be a better one here. There we go, right? You know for a fact that these are a certain age, and so then you know that any other time you find other ones, they will also be the same age, right? So once you find one area that we know these rocks are this old, now you can just use that to say, oh, those other rocks over there must be the same age because they're the same type of rock and so forth, right? And again, I kind of skipped through this real fast, but the older rocks are at the bottom, the younger rocks are on the top. And so again, that's where you get this one, where older rocks at the bottom, younger rocks on the top, right? And there we go. This is how we know the ages of all these fossils, right? So that way we can understand how evolution works. Let me know if you have any questions. Otherwise, I will see you later.